Hey everyone, welcome back to the Medin webinar series. The general theme of this month's webinar is around ocean data at scale. So we were talking about some of the challenges associated with managing high volumes of data and managing data being transmitted in near real time from autonomous platforms. So we have Jack and Katy from BODC to talk about autonomous platform data management at the British Oceanographic Data Centre. And then we have Danny and Monica to talk about high volume data archiving and challenges. There'll be time for questions after each of the presentations, so please feel free to drop your thoughts into the Q&A as we go and upvote other people's questions. And with that, I will hand over to our first speakers, Jack and Katy.
Hiya, can you hear me okay?
Yep, we can hear you.
Brilliant. Just share the screen. Sorry, just give it a moment. There we go. And you can see my screen okay, yeah?
Yep, looks good.
Brilliant, okay. So we'll get started. My name is Jack Jones, and my colleague Katy Baldwin are marine data managers at the British Oceanographic Data Centre, and we're both members of the autonomous platform team at BODC. This talk is going to cover BODC data management practices for multiple platform types, including how we process data, data dissemination, and how we work with the wider communities. So, sorry. BODC manage data from a range of autonomous platform types, which are Argo floats, gliders, and Autosub Long Range gliders, or ALRs. Data come to us in 3 different modes, and that is near real time, which is we'll explore more in this talk, recovery, and delayed mode. So recovery data is the full resolution version of the data that BODC receive once a glider or ALR has been recovered, as only a subset of the data are sent in near real time. And just to note, that only applies to glider and ALR. Argo floats don't produce a recovery data set because they run until end of life. Delayed modes, similarly, are submitted to BODC post-recovery by the scientists, and these include additional quality control and calibrations. So in this talk, I'm going to explain data management procedures for gliders and ALR, and then Katy is going to do the same for Argo floats. So, starting on some basics for glider and ALR deployments. Gliders typically have depth ratings to about 1,000 meters and are equipped with 2 to 5 sensors. Deployments might typically last weeks to months. BODC handle near real-time data from multiple glider deployments at any one time. This peaked in August 2024 when we managed 12 active glider deployments. We expect this number to increase, particularly amidst aims to achieve net zero in the ocean science community. ALRs are much bigger by comparison and are rated to deeper depths of up to 6,000 meters. Their larger size means that more sensors can be deployed on a single platform. ALR deployments also last much longer and can be below the water surface for longer than sea gliders and slocum gliders. Both autonomous platforms transmit data in near real time via Iridium once at surface. And as mentioned, this is usually only a subset of the full resolution data that we get on recovery. Moving on. The first stage of glider and ALR data management at BODC is receiving metadata. Data processing has a strong focus on metadata, applying controlled vocabularies from the NERC vocabulary server and utilizing a semantic sensor network database, or SSN, that I'll mention again later. Metadata, including platform models, sensor models, and the associated serial numbers or instances of those models, are essential to setting up metadata, allowing for near real-time data processing. As you can see on the right, BODC now use a custom-built web-based user interface to input metadata. This is known as PAMS. That's the Platform Agnostic Metadata System. PAMS, as you can see, features a series of drop-downs which are constrained to controlled vocabs, as well as free text boxes, making metadata setup simple and easy. Metadata are stored by BODC on the semantic sensor network database, as I mentioned, and once metadata is set up, BODC can receive source files from the deployment in near real time. It's just a note that prior to the development of the PAMS user interface, metadata setup was a more manual process using SQL posts to our database. It wasn't found to be as fast or user-friendly, and the implementation of PAMS has resulted in a six-fold reduction in the time taken to set up a new deployment. It's something we're always trying to work on and improve. Moving on to near real-time data dissemination. So source files are received and processed at BODC, first by converting to our internal file format, and then to community file formats, that being OG1 and CovJSON, that I'll come on to as well, ready for delivery to the scientific community. Near real-time data are delivered both on the BODC website and via direct pushes of data to stakeholders such as the Met Office. So BODC use the AirDAP file server to make data available on the website. Raw files and community standard OG1 files are available to download. We send temperature and salinity data to the Met Office, who include the data in forecasting models and deliver the data onto the GTS for use by the wider community. And it's just a note that we currently send data to the Met Office in TSAC messages via email, running in parallel with us sending the Met Office CovJSON files. Development's ongoing on our side, and we're hoping to move to a solely CovJSON based system soon. And yeah, just referring to the images, leftmost as an example of the TSAC emails that I referred to, and middle you've got the deployment catalog, which is available on the BODC website, and that links to AirDAP. So link into that. As mentioned, BODC also receive glider and ALR data in recovery and delayed mode. Recovery data, as I mentioned, comes from the SD card once the glider is recovered and are submitted by the platform operator, which is often Mars. BODC decode and reformat the data into segment files, which is one file per dive. And these are combined ultimately into a single net CDF for delivery to scientists. That workflow currently only applies to gliders, but work is ongoing to extend the recovery workflow to ALR in the next year. Delayed mode, on the other hand, they're also received post-deployment with calibrations and quality control applied to the principal scientist, so usually that received at a later date. Also, typically a single file per deployment, which is archived at BODC, and we can process and provide a DOI for use in future publications. So, this slide is just a nice illustration of the lifetime of glider data from source to delivery and use in the scientific community. So from left to right, near real-time data first requires the flow of data from an active deployment with robust underlying metadata, such as controlled vocabs and the SSN database, which I've referred to. Ahead of any deployment, BODC works with the PI and operators to ensure that all metadata requirements are set up in advance, and the glider is ready to send us data on deployments. Data are pushed to the BODC archive and ingested to our internal file formats, which are then converted to community formats such as OG1 and CovJSON. As mentioned, data are also delivered via the AirDAP data server in both raw and community formats. And this is discoverable via the platform deployment catalog on the previous slide, and users can help themselves to the data. Glider data, as I mentioned, are also available in DOIs, again, available for download from the BODC website. And throughout this process, we work closely with glider operators to ensure that everything runs smoothly. We found that this has proven successful in ensuring that the data are consistently delivered to the scientific community, as you can see, for QC, modelling, decision making. The last slide from me is on BODC's role in the ocean gliders community. The community aims to support active coordination and enhancement of worldwide glider activity. BODC sit on the Ocean Gliders programme and co-chair the data management task team with the first adopter of the OG1 file format, which is used amongst the community. And we contribute to Ocean Gliders community standards by advising on OG1 vocab requests and by taking part in discussions on the direction of the community. Just a point on FAIR, BODC aim to handle data in line with FAIR principles to make data findable, accessible, interoperable and reusable in line with the aims of the Ocean Gliders community. And yeah, for your own reference, this presentation will be made available. So yeah, please feel free to visit any of the links to learn more about the Ocean Gliders community and the role that BODC play. So thanks for listening to me. I'll hand over to Katy now to speak about Argo floats.
Yeah, thanks, Jack. So just to reiterate what Jack said, my name's Katy. I'm also one of the marine data managers at BODC, and I'll be covering the Argo side of our talk today. So I just want to start off with a quick introduction to what Argo actually is. Argo is an international research programme with over 30 countries involved, and with each country having their own Argo floats to look after and manage. And so we at BODC are a critical component of the UK Argo programme. Argo measures water properties across the world's oceans using a fleet of robotic instruments that drift with the ocean currents, moving up and down between the surface and the mid-water level. There are currently over 4,000 active floats that are transmitting data within 24 hours, which are freely accessible to everyone. We are currently managing over 150 of these active floats at BODC. The main objective of the Argo programme is to create a fully global, top-to-bottom, dynamically complete and multidisciplinary One Argo programme that will integrate seamlessly with satellites and with other in situ elements of the global ocean observing system. So just looking at the bottom left of the slide, the diagram shows the cycle of a float. A float is deployed off a platform, and once deployed, it will then descend to its drifting depth of around 1,000 metres, and it will stay at this depth for around 10 days. After that 10-day period is up, the float will then descend further to its profiling depth, and this depth depends on the type of float that's been deployed. Once at the profiling depth, the float will begin to rise to the surface, collecting specific measurements within the water column. And once the float reaches the surface, that's when it will transmit the data to a satellite. It's important to note that unlike gliders and ALRs, Argo floats are not recovered. They continue profiling until the end of their lifespan. So I just mentioned that the profiling depth depends on the type of float that's been deployed. So we have core Argo floats, and these floats collect the standard pressure, salinity and temperature measurements at a maximum depth of 2,000 metres. And then following advancements in platform and sensor technologies, additional sensors have been added to Argo floats in recent years, allowing them to collect biogeochemical, so BODC parameters, such as dissolved oxygen, pH, particle backscatter, irradiance and chlorophyll A, as well as the standard core parameters. And then there are also the new deep Argo floats, which can measure at depths of up to 6,000 metres. These advancements have massively improved our understanding of oceanic cycles of carbon, nutrients and ecosystems. So once a float reaches the surface, it begins to transmit the near real-time data to satellites, which begins the automatic retrieval process. However, before a float is even deployed, it's essential, just like with gliders and ALRs, that we have documentation, so the relevant metadata for each specific float already loaded into the BODC systems. And how we do this for Argo floats is the float manufacturers provide us with the documentation, and we load this into our database using SQL Developer and several different Python and MATLAB scripts. This metadata includes the likes of WMO number, PI name, platform, deployment platform, sensor serial numbers, and so on. And just with that being said, I wanted to highlight some work and discussions that have been going on for quite some time to make this a more automated process. The Argo community have been working with the float manufacturers to produce a standard machine-readable MetaJSON file for floats, platforms and sensors, instead of having to put this information out and manually add it to our database. And so this then led to the development of the metadata validator tool, which essentially is a Python-based tool to validate the metadata JSON that will be provided by the manufacturers. This tool will be a way for manufacturers to check their metadata files to ensure it includes all of the relevant information in the correct format prior to submitting them to us, and for us to validate the metadata file before it's added into our database. The key features of the validator tool are that it checks the compliance of the metadata with the NERC vocabulary server, the MVS, and reports any errors in a clear and structured way. A final piece of work was completed in a development sprint last week that enabled the metadata JSON file to be read into our database. And it's this work that will enable us to hopefully start testing the next batch of floats in 2026. And we'll be asking the manufacturers to provide us with this metadata JSON as well as the documentation as a backup. The ultimate goal of this will be a seamless and automated end-to-end workflow. So moving on to the actual Argo data processing procedures at BODC. Once the float transmits the data at the surface, it is automatically retrieved from the Iridium and Argo satellites, and it arrives at the data assembly centres, referred to as the DACs. And there are 11 DACs in total globally. BODC are one of these DACs. The raw data is automatically archived and then passes through our real-time processing systems, where it is subject to a number of different real-time quality control tests. It's flagged accordingly and then converted into netcdf files via internal MATLAB scripts. Each profile that we receive is converted into a profile netcdf file and also a technical trajectory and metadata file. The metadata file is generated using a combination of the raw data that we receive from the satellites and the metadata that's already in our database, which is why it's so important to already have it loaded pre-deployment. So just providing a little bit more information on the quality control procedures that are done on near real-time data. On the left of the slide is a list of the different real-time quality control tests that the data are subject to as they pass through our processing systems. All Argo data is flagged, as all our data are subjected to a minimum of the real-time quality control tests, and the resultant flags are also vital to understanding the context and reliability of the data. And so that being said, I've also included a table containing the different Argo QC flags and what they mean on the right of the screen. And just whereby 1 means that it's good data, 2 means probably good data, the 4 flag means bad data, and 9 is the flag used for missing data values. Real-time data is the first form of Argo data available to the public. Because of the requirement for delivering the data to users within 24 hours of the float transmitting its profile data, the real-time quality control tests are limited and automatic. Individual real-time profile data files will have an R suffix to identify that it is real-time data. Some real-time parameters, like the BGC parameters, are automatically adjusted by comparing to the reference data, so ship-based hydrographic data and world ocean data. And this is done to remove any bias due to instrument errors or various technical issues. These data are not replacing the original data. The raw data are never changed. Instead, an adjusted version of the parameter is created. And then we also have the delayed mode quality control procedures. And delayed mode QC processing is the set of analysis based on statistical methods, and these methods differ between core, BGC, and deep. Argo data are compared to reference data and other climatology datasets, as they should show consistency across similar temporal and spatial ranges. The float analysis requires scientific knowledge and expertise from specific ocean regions to estimate the quality of the data with the associated error. It's been recommended that delayed mode data inspection is carried out 1 year on a 1 year long record, so that sudden jumps in calibration may be distinguished from long-term drift or water mass property changes. This imposes a minimum of a 6-month delay on the availability of the delayed mode data. And just like with the real-time adjustments, delayed mode data is also compared to the reference data to remove any bias, whether this be due to instrument errors or a technical issue. Again, the adjusted data are not replacing the original data. And delayed mode data profiles can be identified by a D suffix. So then where does the data go once it's gone through our system? The UK Met Office collect the NetCDF files from our systems, and they provide the data to the GTS in under 24 hours from data generation. The Met Office convert the NetCDF files into buffer files, and this is what they supply to the GTS. And then the data then further reach operational ocean and climate forecast and analysis centres via the GTS. We send all of the data to the 2 global data assembly centres, so the GDACs, again in under 24 hours of data generation. These 2 GDACs are USCADA in the USA, and this will be replaced by NOAA in the near future, and IFRAMET in France. All Argo float data can freely be accessed from either of the 2 GDACs using the links on the slide. The 2 GDACs synchronise their data holdings daily to ensure consistent data is available on both sites. IFRAMET run additional quality control tests on the data that are not performed during the real-time quality control tests in the BODC systems, and they will let us know if the data fail any of these tests, and then it's up to us to reflag the data accordingly. This is known as objective analysis. The BODC Argo team members are members of the global Argo data management team, the ADMT, and it's the role of the ADMT to coordinate the data management activities for Argo to ensure an integrated access to Argo data independent to where it's processed. The ADMT is composed of at least 1 member of each institute involved in Argo data management activities. The ADMT defines the Argo data management infrastructure and role of each component, the data format and its evolution, and the quality control procedures and delayed mode procedures. This provides structured governance and helps to provide a framework to support best practices and continuous improvement within Argo. So that's everything from me. Thank you very much for listening to us both today. I think we do have some time to answer some questions, but also please feel free to reach out to us using either of the email addresses on the slide. So thank you very much.
Thanks both. As always, if anyone has any questions, please feel free to type them in the Q&A. There's been a couple that have come through as you've been talking, so I'll just read those out for you. So the first one is, if an Argo float drifts with ocean currents, is there a risk that all the floats will end up in the main currents rather than widely spread? Can they be directed to a new location once deployed?
Well, they aren't piloted like gliders or ALR, so yes, I suppose there is a risk of that. It's up to each country where they're deployed. I'm sure one of the player or DAC lead could probably give you a better answer for that. So if you do email the Argo team, I'm sure somebody could get back to you with some more specifics.
Thanks, Katie. They are very widely spread, aren't they? So I think if they probably notice that there's a large clump of floats that are getting stuck in one particular current, they can deploy more in other areas to make sure that there's a good data coverage. Okay, thank you. So the next question is, what are the main challenges of maintaining autonomous platform near real-time data management, and what have you developed to resolve them?
Shall I start with that one? Okay, yeah, so a few challenges come to mind that sort of touched on a few in my presentation. So metadata collation prior to a deployment, making sure that we provide consistently running systems would be another challenge. Let's say aligning with community standards, and I'd say another one is to try to make data fair, as I mentioned. So yeah, we'll try and touch on how we've resolved each of them. So we've developed the PAMS dashboard, as I mentioned, to help with metadata collection prior to a deployment, and this is aided by close collaboration with the operators. As I mentioned, this has made metadata collation, much more efficient for the team to complete. The glider team also constrain much of our metadata to community standard control vocabularies, that being OG1, ensuring that our work aligns with the community. The use of controlled vocabs, touching on fair, also contributes towards glide data being interoperable and reusable by the community. And we try to make the glider data findable and accessible by making it available on the BODC website in the ways that I explained. In terms of keeping consistently running systems, I didn't touch so much on the glider monitoring dashboard, which BODC have developed. This allows for monitoring of active deployments to take place at a glance and in a single place. Processing and delivery statuses are time-stamped and color-coded on the dashboard, and that just allows the team to quickly recognise and flag any issues to have resolved. So, so the development of that tool helps us to keep near real-time systems running pretty consistently. So yeah, that's everything I can think of really. So anything for you, Katie?
No.
That's great, thank you.
Thank you.
So I guess there's a similar question for Katie that's also come through. What are the main challenges that BODC face as an Argo data assembly centre?
Yeah, so one of our main challenges is funding for new Argo floats, and ensuring when we do get new Argo floats that the data management is also funded. And then another challenge that we have is ensuring the timeliness of the data to the GDACs. So if there's any problems with the systems that come up, that affects the timeliness. And so we've trained a lot more people recently, a lot more members of the autonomous platform team, so that they're able to also work on the Argo daily processing to pick up on any issues, just to make sure they're resolved as quickly as possible to ensure that the data is being sent to the GDACs on time.
Great, thank you. And then there's a couple of questions on the JSON format. So someone asked, what was the JSON format that was mentioned a few times? Was it COB.json? Then someone's also asked, you mentioned COB/JSON, I think, format for data files. Is that an internal format or something that can be shared?
Yeah, so sorry, COB.json, that's cut short for coverage JSON files. I believe these are community file formats. It's basically just what's been requested of BODC by the Met Office. So the data that I'd say we disseminate to the wider community tends to be in either raw format or OG1 format. Coverage JSON files, I believe, are produced to be specifically sent to the Met Office at this stage. If that answers the question.
Okay, great. Yeah, I think so. Hopefully it does. And if not, we can possibly maybe dig out some more information to send with the follow-up email later on.
Yeah, I'm more happy to do that.
Great. So if there's no more questions for now, we can move on to the next presentation. And if any more questions come through in the meantime, we can answer them at the end. But for now, I will hand over to Monica and Danny.
Thanks, Rosanna. Just moving that out of the way. Okay, so my name is Monica Hanley, and along with my colleague, Danny Wright, we're going to be talking a little bit about high volume data and its challenges in data management with a specific view of what we're doing here at BODC. So first and foremost, what are we talking about when we say high volume data, and what's actually the problem? So in this specific case, we're talking about 100 gigabytes and above. So I appreciate everybody has sort of a different definition of what high volume is, but this is high volume on the basis of what we can handle within our systems here. And we're talking about going up to hundreds of terabytes worth of data. So obviously transferring data of this size is quite difficult. There's challenges from getting it from the originators to the data centers, and it can be very slow, require lots of manual steps. Our normal data upload routes are not sufficient, and they can break our servers. And similarly, access by end users is met with equal challenges. So typical online download mechanisms can be very slow. Users may think downloads have timed out, but it's just taking time to process the data. And users often won't have the space required on their own machines to actually download the data and then process them with something meaningful. So there's lots and lots of infrastructure and architecture considerations that go along with high volume data. And governance and security of the data is always a challenge as well. So what are the different types and formats we actually get at BODC? The main ones we get are model outputs. So we want these to be in netcdf files, preferably CF netcdf, which stands for climate and forecast netcdfs. Then we have geophysical data such as bathymetry and seismics data, which we ask for in SegWi, XYZ, or TIFF formats. Then we have passive acoustic data, which comes in WAV, and video and imagery in MOV and JPEGs. So as always, we ask for non-proprietary file formats with rich metadata to go alongside the data, as we aim to maintain a standard level of metadata and delivery and data security. So once we get these large volumes, how do we actually store it? So we're lucky here at BODC that we're part of the NERC Environmental Data Service. So along with the other data centers that make up the EDS, we can sort of help each other out and use each other's infrastructures. So luckily we have CEDA, which is the Center for Environmental Data Analysis, and we can utilize what already exists with them. So they have petabytes worth of storage available for us to use, and this is because they're sort of intertwined with Jasmine, which is the UK supercomputer for environmental science. So essentially, they're already equipped to handle this type of data. So instead of trying to invest loads of money and resource into doing it ourselves at BODC, we are sort of tagging along with CEDA. So we then have RODEM, which is our tape storage, which is hosted at the National Oceanography Center in Southampton. This is much more cost-effective and environmentally friendly. So it may take a few days to get the data back off the tape storage, but if it's not data that's being requested a huge amount, and it doesn't need to be readily available for end users, then this is a really good option for us. Sometimes we'll just publish a subset of the final product for one-click download, which references the rest of the data. So for example, if we have lots of raw images, we could put the high volume raw stuff onto the tape storage and then just publish a subset of fully processed versions to publish in a DOI. It all sort of depends on what has the most value to an end user in the wider community. We also have a data retention policy. So this dictates that where possible, data are either removed or moved off to cold storage after a period of time. The standard is about 10 years, and this mainly applies to model data because often model data has sort of advanced within that 10-year span. And we do ask for internal compression of files where possible. Again, this is mainly for model outputs in NetCDF format, and we've seen a huge decrease in volume by applying some internal compression tactics with very, very little impact to the end users. So that's always good. So a little bit about model data management specifically. Metadata are submitted to BODC via our submission app, which is our standard route for all submissions. And a DOI is created pointing to the data archive. Our archive system can now track external archives. So if the data aren't sitting within our own spinning disk, we can still point to where that data is. So obviously the data are much too large to be submitted through our submission app. So the data are generally uploaded onto CEDA by the originator themselves, or if the data are sitting on a group workspace in Jasmine, we can actually go straight into that group workspace and pull the data and archive it there on CEDA. So there are a few different model scenarios that we come across. First and foremost, we have models that are used to test a specific hypothesis, and these outputs have little long-term value to the wider community. In these scenarios, we don't archive anything because, as I said, we focus on the impact to the wider community, and if there isn't much value, then no need to archive. We then have easily reproducible outputs if code and input variables are provided by the originator. So in this case, we don't archive any outputs, and we'll just point to code published in a code repository such as GitHub, which has been DOI'd for that specific instance of code. And this is for scenarios where, say, you could run the code using open source software or something, and the outputs aren't going to be too big, and an average end user can do it based on the information they're given. Most often, we get not easily reproducible outputs that do have long-term value. So again, we publish the code in a code repository with a DOI, and then we will archive either all the outputs or just key outputs. So sometimes we'll just archive a specific time resolution or a specific run. But this will be a conversation that we have with the data originator to figure out sort of what they need to publish their papers and what's actually going to have the most impact to the end users and the wider community. So that's a very, very high level overview of the model stuff. So now I'm going to hand over to Danny, who specializes in some other types of data, to explain a bit more about that.
Thanks, Monica. Yeah, so I'm just going to talk a little bit about sort of the geophysical data management at BODC and sort of focus on just a few of the main types that we get. So yeah, so one of the main types is bathymetry data. So typically via our normal submission app route, there's sort of a file size limit of about 250 megabytes, I think. And in most cases, the sort of final process data that we like to make available to users is sort of at that limit or just above. So we do tend to have to go down, non-standard routes to receive the data. So we will normally expect to see processed files in sort of non-proprietary formats such as XYZ, TIFFs, or DTM. We do like to store the raw formats in their proprietary formats, and that's usually stored offline in the tape servers. It usually comes straight off the ships normally in that format, so we can just store it straight away offline. And yeah, we like to make those files available to EU and international products where available. So any data that falls within the EMODNet regions, for example, we'll make available there, and the same to GEBCO as well. So for seismic data and generally any other types of geophysical data, we do encourage, as Monica introduced, we do encourage people to submit those files directly to CEDA, where we can then pick them up from our archive area and then publish with links back to DOIs. And again, we like to store the raw formats offline and make them available on request as necessary. Yes. Next slide. Thank you. The next one I want to talk about is video and imagery data management. So as we sort of already covered with Jack and Katy, the NOC operates a whole fleet of ROVs and AUVs. And in this sense, they offer great platforms for sort of deep benthic camera surveys. And obviously, each mission can be sort of a few terabytes worth of data. So all of these raw images and videos are archived post-cruise straight offline onto our tape server. And there's normally quite a bit of conversations with the PI about what subsets they might want to make available. And again, we encourage them to submit them straight to CEDA nowadays. And again, we can publish those with DOIs. We do have a new route for the submission of imagery metadata in the image fair data object standard now, and then users can do that via our normal submission app. Yes, so we will have a link between the metadata and then where the images or video actually sits at CEDA. Next slide. Yep, so it's just to sort of quickly wrap up the future of high volume data at BODC. So we are having to constantly evolve our workflows and how we manage all of this data as we get, I think, ever increasing volumes and data types in. There's always new technologies which are sort of developing at a very fast pace these days, and we need to be very adaptable in addressing how we handle all of these data types and make sure that we are conforming either to existing data standards or making sure that we're involved in the conversations with associated communities in developing new standards. And that's been particularly evident in the imagery side in the last year or two. We also still face challenges in what exactly we do archive, whether that be the raw data, processed data sets or products, and also where we store those data. And all of this can often depend on those data types as well, particularly because maintaining data online on spinning disk is very carbon intensive. So it is more environmentally friendly to store certain things offline, which is why we've spent quite a lot of time now just storing sort of the raw side of things onto the tape servers. But yeah, it's a conversation that we're always involved with. So yeah, data are always getting higher. We're always getting higher and higher volumes of data, and at a very fast pace nowadays. So yes, we face ever evolving challenges. Yeah, I think that's about it. Thanks very much.
Thank you. As always, please feel free to put your questions in the Q&A. Let me just refresh if anything that's come through. And so many questions. I'm trying to make sure I've got all of them. Okay, one's just come through for this particular presentation. So what's the most common way originators actually give you the data, given the challenges of moving large volumes?
So it sort of depends on the route it's being on where it's being archived, rather. So if it's going to CETA, we will use CETA's systems, and they actually can give users bespoke rsync commands to be able to just rsync the data across from the user's computer straight onto the CETA arrivals area, where we can then pick them up, and that's secure. It'll give them a temporary password and all that sort of stuff. We can do the same to get the data in at NOC, to put it on the tape storage. If it's generated by NOC scientists, we can generally put it on the NOC servers and just pick it up from wherever it's sitting. Occasionally we'll get hard drives mailed in. We don't get these very often, but it does happen. And if we're talking about huge volumes, hundreds of terabytes, we can look into using Globus. That's integrated within the Jasmine systems, I believe. So that's one way to do it as well. So yeah, like I say, it sort of depends on the data type and where it's going to sit. But I would say the most common is the use of rsyncs.
Thank you. And then kind of a follow-up question is that, so if people wanted to submit high volume data to BODC, how would they go about doing that? Who should they contact? I think
I can probably answer that one. So generally, if it's related to a project that we already might have data management funding for, there is normally a BODC designated person associated with that project. So that would be the person to contact. You should sort of know who that is, I think, if you're sort of leading on the project. But if not, then there's always the general inquiries at bodc.ac.uk email address, and that goes straight to our request team, and they can then forward that on to the relevant person. But all of this sort of discussion about what data might be produced and where it might sit should all really be done at the data management sort of planning stage. So we should be quite informed. But if it's legacy data or not a project that we're associated with, we can still have a chat about what options there might be. So yeah.
Thank you. Another one's just come through. So how long does it take the data to reach eModNet once you get access to it? And do you have an average from collection to eModNet?
Yeah. So normally from the time we receive data that we know is going to be sort of earmarked for that project, it's sort of like there's a 2-year funding call that happens. So they release a new product every 2 years. So it depends, I suppose, exactly when that data was submitted as to when exactly it will be made available. But we do make it available. We ingest it ourselves anyway. So it's usually available via our own All Series app before it reaches eModNet. It might not be available via eModNet for another year, sometimes 2, depending on when it gets to us. But we're halfway through a round at the moment. So I think the next release will be the end of next year or early 2027. But yeah.
Great, thank you. I hope that answers the question. I did notice there was a question that came through. I think it was for Jack and Katy. I'm not sure if they're still around to answer questions. I'll read it out. I think it's kind of been answered a little bit. We've been going on anyway, but I'll read it out, and if you have an answer, we can maybe add to that conversation. So once NOC has pushed the data to GDAX, I'm assuming this is Argo related, is the raw data needed to be retained at BODC, or is it deleted, for example, to reduce the carbon footprint? Yeah, I'm not sure if you have an answer for that one.
Good question.
Yeah, I'm pretty sure we keep the raw data. I presume Camilla would be best to answer this for the DMQC side of things, but I don't think we delete any of the raw data.
No, I think it's archived, isn't it?
Yeah,
Yeah.
it's archived.
Thank you. Refreshing the question, see if anything else has come through. Don't think I can see anything. Please let me know if I've missed something. Notification. No, okay. I think we've answered all of the questions that have come in so far. So we'll start to wrap up if there's no more questions. So huge thank you again to our presenters for today, Jack, Katie, Monica and Danny, and thanks to everyone that's come along and asked lots of questions. It's been lots of conversation today, so that's been great. If you have any feedback about this session or the webinar series as a whole, please fill out the feedback survey. I'm starting to look ahead at the next phase of the webinars and our training offerings in general. I'll be using the feedback received to inform what that might look like. That's really useful if you fill that in. Coming up on the 21st of January 2026, same time, so between 2 and 3 p.m. is our next webinar, which is about unlocking ocean knowledge, the global push for better data sharing. So that'll be all about global data sharing initiatives and the landscape of data sharing and where Medin fits within that. We've got some really fantastic speakers lined up, so that should be really informative and interesting. We also have an online workshop coming up in February. So if you want to learn more about marine data management, governance and the Medin toolset, you can come on to that. There's more details on our website for how you can sign up for that. So thanks again for coming today. I hope you've enjoyed the session and learned something new. Have a great rest of your day and a restful festive period. And I hope we'll see you again in the new year.